Thank you very much to the organizers. Thank you to Vito, to Rock for inviting me to be part of this space where we share some mathematics. So I hope you enjoy this presentation. I will present some examples or where to find or avoid order. I hope maybe you know them. Maybe it's nice to refresh the memory, and I found them very nice. So that's what I wanted to bring them today. So before I start with the examples, so let's start with the question of what does chaos mean? So we will talk about chaos and order, but where? Because it's not the same if I talk about chaos, I don't know, in my mind, in life, in the room. So we need to find what does it mean for us. And doesn't matter where you ask this question, usually what does it mean that something is chaotic or that something has chaos? Where you cannot find, at least I think in general, we cannot find a pattern, or we don't know much information about this structure, or depending where are we asking. So the opposite of the chaos will be the order. But again, what does it mean to have order? It depending, or when are you asking this question, to who are you asking these questions? And for us today, we are focusing in mathematics. So we will try to find some concept of chaos or order. And even if we just focus on mathematics, it depends in which area of mathematics are you asking this question. So this is what I will try to give you a little bit of flavor of what order means in some structures. So as I say, I will give you some examples. Let's start with the first one, which it's called the party puzzle. So I will put it here first. And this friend and stranger problem, the question is, what is the minimum number of guests that must be invited to a party so that either a group of 3 people will know each other, or at least 3 guests will not mutually know each other? So basically, how many people you need to put in one room so you can be sure that 3 of them will know each other, or 3 of them will not know between them, okay? And what is the minimum number? How can I turn this problem into an area of mathematics? Let's put 1 point for each person. So let's say I have this amount of people in the party or in one room. And now I will put 1 line between 2 people, or 2 points in this case, if they know each other. And if they don't know each other, I won't put any line. So let's say I have this structure. This is also called a graph. So maybe if you have been around FAMNIT, you know that this is a really object of study of many people here in FAMNIT. Also, I work on graphs, and today I will try to don't use many definitions or very technical words. So just very informally, what is a graph? A graph is points, and I will put a line between some of these points. In this case, if there are people and they know each other. And we have many different kind of graphs. So very simple, just keep in mind for today, we want to be working with points and lines. So now I turn my problem from this party to a graph. What does it mean, this problem here? So if 3 people will know each other, what does it mean? If three people don't know each other, what does it mean in this figure? Well, this means that I will have either this structure or this one. So here, the three people know each other, and here, these three guys, they don't know each other. So we want to know if in this graph, in this example, I can have either the triangle or the 3 points that are that they don't have a line. Do we have this structure here? Well, if you are fast, you can see that there are many of these examples of, for example, these three, they don't have a line between them. And you can find much more, right? These, and these, they don't have line between them. So we can find one of the two structures. But the question is, can we avoid these structures? How can we avoid these things? How many people, how many points do we need in order to put, to know that I won't have them? If it's possible, does it matter how I put the lines? So can you give me an example where this doesn't happen? Can you think in one example where we can avoid this? Well, one simple, it will be exactly this without one line. So very easy, 3 points without this line. This means that three people, these two will know, these two will know, and this no. This is another example. So in this case, if we have this graph, we cannot find for this graph or this graph. So we will go back to this problem, the party problem. But before that, I want to bring you to another example. I promise that they are related. Just follow me with this game. So for this game, we will need 2 players. Each one will choose one color. Let's say red and blue, any 2 colors. And then we will start with a complete graph with n points. What is a complete graph? I put you here examples from 2 till 7. So a complete graph with n points, let's say here 6 points, it means that I have n points, 6, and all possible lines between them. So I will start with one of these graphs, depending of how many points I want. So I start with one of these, and then how we will play. Each player will color one line in one turn with its color. Who will be the winner? The player who managed to create a monochromatic triangle. So if I manage to have the red triangle or blue triangle, I will win. And the question here is, do we always have a winner? If we play, doesn't matter how big is the graph, how many points we have, 100, 20. Do we always can say that it will be a winner? And the answer is no. This is a very small example. Here we have 4, if we start with 4 points, and these 2 players play in this way, there is no winner. We don't have a blue triangle or we don't have a red triangle. So we don't have a winner. But if I have more than 5 points, there will be always a winner. How can we prove this? Well, one way of proving this is I take at least 6 points, and then I go through all the possibilities. So we have this number of possibilities. We could try, but there is a better way. And this was this was done by this mathematician, Ramsey, in 1928. And the proof is very nice, so we will go through it. And let's imagine that we have more than 5 points. So it doesn't matter how many points we have, at least we have more than 5. But we need just more than 5, so let's keep 6. So keep in mind that we need to put all possible lines between these two, between every point in all the graph. So we will put a line here, here, all possible lines. So every point here will have at least three lines of blue color or red color. It's not possible that I have two, that this point has just 2 red and 2 blue, because it has to have a line 1, 2, 3, 4, 5. So if it has 2 blue and it has 2 red, it's not enough. So every point will have at least 3 red or 3 blue. Let's take this point and let's choose red. So this point will have at least 3 red. Now, what can we do? We will try to avoid triangle or a blue triangle. How can we avoid? Here, I need to put a line. If I put a red line, I have a triangle. So it has to be blue. The same for this one. If I put a red line, it will have a triangle. So it has to be blue. But now what happened with this line? Doesn't matter which color is, I will have a red triangle or a blue triangle. So every time we have, every time we have more than 5 points, we will have this configuration. So we cannot avoid this. I will go through it. So now, if we go back to the first example, to the party puzzle, how is this related? Well, we have this graph, and we started with lines. So let's call them black lines. And the lines that are not there, let's put it one color, invisible color, blue color. So in this case, if we have the black lines and the others that are not here, we have, or one black, we will have one, since we have more than 5 points, we will have or a black triangle or a blue invisible triangle. Okay? So we know if we have more than 5 points, we cannot avoid, or in this case, a triangle or an empty triangle. But we don't want just to know if we have it. The question was, what was the minimum number? So what we need to know in order to have a minimum, we need to check that we can avoid this with 4 points, 5, 3. And we already did that. We have this with 4 points without this configuration. We have this example before without this configuration. And of course, the most simple with 3 points. We can avoid this. So we know the answer is 6. We are happy with it. We prove it. So every time you put more than 6 people in one room, you will find 3 people that know each other or 3 people that don't know each other. We start with this small example, but once we prove it, once we understanding, once we know it, what do? Well, usually when you have this kind of samples, you try to ask for more, even larger numbers or a generalization. And this is what it happened with this problem. So now, again, the question is the minimum number of people that needs to be in one place so that our people will know each other or these people will not mutually know each other. And these numbers are called the Ramsey numbers. So I mentioned this mathematician before. Of course, when he proved this, didn't have this name. This was developed afterwards. So what we did before, it was to calculate r, small r, S 3, 3. And we prove that this number is 6. We're happy, we have a Ramsey number. But what happens if we want larger numbers? Here, maybe you cannot see very well with the colors, but we have a graph with 17 points and 2 colors, also red and blue, but it's really hard to see. And I promise you that there are not 4 points with all possible lines blue or all possible lines red. And this was proof. And when you increase the numbers, things get not so easy to prove. And even Erdős tried to prove some of these numbers, give some of these numbers, or at least put some lower bounds for these numbers. And you will see, okay, if I have 3 people in one party or in one room, how can this be useful? It is, I promise you, that you have a lot of applications on networks and networks for social communication, transportation, etc. So these kind of structures are important to know when you can avoid them or when you cannot avoid them in order to optimize the number of points that you have in one network, for example. How difficult is to calculate these numbers? So we saw already one, we did here one example, but how hard it is. So this is, if I'm not mistaken, the last table. I didn't fill this because it's the same if you put RS or reverse the numbers. So for some numbers, you have a specific, you know the number, how it is, 9, 14, 5, 4 is 25. But these ones that you have here, there's people working on trying to calculate them. And if they cannot give you one number, they use probabilistic methods, numerical methods in order to increase the lower bound or decrease the upper bound. So it's not an easy task, because when you prove it, what you need to do, well, basically 2 parts. You need to prove that when you give the number, doesn't matter how you color the graph, doesn't matter how random is your color of the edges, you will always have what the structure that you are asking. And once you have that, you also have to prove that you cannot do it with less. So things are not so easy when the numbers increase. I mentioned before, this is the mathematician Frank Ramsey, and he started to work on this. And later on, Paul Erdős, he continued, was one of the things that he was working on. And later on, the theory was developed, the Ramsey theory. So this was the beginning of the idea of this theory. And what is the philosophy of this theory? Is to try to find some order, some information, some structures that you cannot avoid appearing among the apparent chaos. And what they mean with chaos, it means that with the random coloration, with not knowing the position of certain points, we will see one example of that. So this is the philosophy of the Ramsey theory. Another example that also Erdős was part of it, that I want to talk, is the happy ending problem. And this was a work done by Paul Erdős and George Szekres, sorry for my pronunciation. They are from Hungary. And Esther Klein, she came with this question. Is it true that any set of 5 points in the plane in general position has a subset of 4 points that form the vertices of a convex quadrilateral. Don't worry, I will tell you in the informal way what is general position meaning. So it means that I don't have 3 points in one line. These points are not in general position, because if you see these 3 points, they are in a line. So this is not what we want. So we want 5 points that are in general position. And what does it mean, a convex quadrilateral? It means that I have to be convex. It means that if I have my quadrilateral, if inside I put 2 points and I make the line between them, it will stay inside. For example, in this case, if I have these 2 points and I make the line between them, I go out of my quadrilateral. So we don't want this, we want this. So it's possible that doesn't matter how I put 5 points in the plane, as long as they are in general position, I always have a convex quadrilateral. And here I have some examples. So here I have convex quadrilateral, here also, and here also. And basically, this is the proof. Why is that? Because here I put it in a I draw the points in a nice way, here also. Or we have basically three possibilities. Or we have 5 points that are already in a convex position, which means that, again, inside here, every 2 points will be, if I mark the line, it will stay inside. So if I have 5 points that are already in convex position, it's easy. I have my 4 points forming the convex polygon. Or I have 4, and this is what I was asking, or I have 3. And if I have 3 of them, the remaining 2, they will form the convex polygon that I was asking for. So these are the only possibilities. Just you can draw it differently, but basically these are my possibilities. So yes, doesn't matter how you put 5 points in the plane, in general position, you always will have these 4 points that will have a convex polygon with 4 sides. And again, what we do, we have small example, we prove it, we ask the next question. Can we find for a given n number a constant fn such that any set containing this amount of points in general position is possible to select n points forming a convex polygon? We did it with 4, so we say that it's 5, but not really, because I mean, we prove that with 5, we always have it. But again, we need to prove that we cannot do it with less. So we already did it. In this example, we have 4 points in general position, and it's not a convex quadrilateral. Also for 5, trust me, it's 9. And I can give you here one position of 8 points. And maybe it's not so clear, but they are in general position. And I cannot find a convex polygon with 5 sides in this configuration. So we have for 4, we agree is 5, for 5 is 9. And turns out that we have this, this number looks, we can find a formula for this number, these 2 numbers. So it's nice. And what did they conjecture? That for every n, you have the number. This is not proof, but they prove that it exists. So for every n, there is a finite number that we can, for which we can find this configuration. But it's still a conjecture. The last number that was found was for 6, and it was by using computer in 2006. And for all the n larger than 6, we don't know the answer. And I think at some point, this I don't know, but they were offering money in order to prove the conjecture. Again, what you have to prove, you have to find the number, which doesn't matter the configuration, how you position the points. As long as they are in general position, you can have the convex polygon with the number, but you have to prove that you cannot do it with less. And of course, I almost forget why it's called a happy ending problem, because yes, Esther Klein was the one that suggests this problem, and later on, Paul Erdos and George were the one working, but in the end, not when they published, probably later, these two mathematicians got married, so it's known as the happy ending problem. So let's move on to another kind of structures, in this case, arithmetic progressions. And don't get scared with the name. What does it mean, an arithmetic progression? It's just a bunch of numbers that you can guess what is the next one. So I will give you some examples here. Of course, if you have 1, 2, 3, 4, 5, 6, you know which one is the next one. Here, after 3, you can guess what is the next one, and so on. So it's a sequence of numbers such that differ between consecutive terms is constant. For us, we will work with this arithmetic progression. And here, what is the example I want to see? If I have the numbers from 1 till 9, 1, 2, 3, 4 until 9, and I color them with 2 colors, with 2 different colors, I can find 3 of them that are in arithmetic progression. So let's color these 9 numbers with 2 colors, and doesn't matter how I color them, can I find 3 integers that are in arithmetic progression? In this case, yes. If you check 3, 6, 9, they are in arithmetic progression. Can you find another example here? I think 1, 4, and 7. So that they have the same color and they are in arithmetic progression. So here we can find at least 2 of them. But how can we be sure that always we have this? We have with 9 numbers coloring with 2 colors, we have 2 to the 9. So it's doable. We can try all possibilities and check that we will find in each of them, but we don't want to do that. So let's keep more simple, and let's try 2 cases. One case, let's say that I color 4 and 6 with the same color. So it doesn't matter which color, red or blue. And now, how can we continue in order to avoid the 3 integers in arithmetic progression? Well, it's easy here. The 5, if I don't want to have the progression 4, 5, 6, 5 has to be red. So I color red. Then what is next? Well, I don't want to have 4, 6, 8 or 2, 4, 6. So I color 2 and 8 with red, but I have already the arithmetic progression. So if I start with 4 and 6 the same color, I cannot avoid this arithmetic progression. So let's find the other case. What happened if I color them different, 4 and 6? So 4 and 6, doesn't matter which color. Again, 5 has to be colored with one of them. Doesn't matter if it's red or 6, the logic is the same. So let's color with red. And again, we know what happened with the 3. We need to color in blue because otherwise we will have the 3 of them in arithmetic progression. And we can continue like that, right? Here, this has to be red, otherwise I have 3, 6, 9, and so on. Then here I color the 7 because otherwise I will have 4, 7, 9, and the 8 because I will have 6, 7, 8, and the 2 because I will have 2, 5, 8, and I don't want 1, 2, 3, so I color in red. But again, I cannot avoid 3 numbers that are in arithmetic progression. So I just have these 2 options. And once again, we can generalize this. And this was done for this mathematician in 1927. So for any R or S, there exists a number such that if we color not with 2, we did it with 2, but if we color with R different colors, then we will find S integers in arithmetic progression. So we did it for 2 colors and for 9, for example, but again, this is something that it can be done much, much larger, in much more larger scale. And here are some numbers, and we can see the numbers that are known. We did this one here, or we proved that we always have it when we have 9 numbers. We always have 3 in color with 2. So this is what we did, but now we did it for 9. But how can we know that we can avoid this with less numbers? If we remove just the 9 here, I think, yeah, the 9 here with 8 numbers, we cannot find 3 numbers that are in arithmetic progression. So the number here is 9. So again, something that is simple to explain with 2 colors, or like with 2 colors, and we can prove easily what is the number. When you start asking for bigger structures or more complicated, then things are not so easy to prove. And I will go through my next example. Again, we will try to find a solution. And I'm talking here about colors. And for these examples, we start with 2 colors. But keep in mind that even if it's just 2 colors, here we are talking that doesn't matter how we color, how random is the coloration, like the color of the structure, we always find these patterns. And this is something that in big scale is used in, has more, it's more difficult to find it in a bigger scale. Here I will talk about this very simple equation, just x plus y equals z. We want a solution of this linear equation. We can think a lot about a lot of examples here. 1, 2, 3, 1 plus 2, 3, 1 and 2, 1, 1, 2. And here the question about finding patterns or finding structure, it was done by Joule and his theorem. And again, he was talking about a cake coloring, so 310 colors. So for all K, there is a number such that any cake coloring of 1 to 3 until that number, we always will find a monochromatic solution of this equation. So it doesn't matter how many colors you want to use, you will always have one number that you will find, doesn't matter the coloration that you use, you will always find a solution that is monochromatic. And the minimum number that you can do this, it's called the Schur number. So here we have some examples for one. So if I want to use one color, maybe if I put it here, it's easier. So if I want to use just one color, well, 1 and 2 are enough because I have just one possibility. If I want to use 2 colors, I have 32 possibilities with 5, but you can color these 5 as you want. You will always find a solution for this equation. So if we change the 3 to black, we will have 2 plus 3, 5. So doesn't matter which one of the 32 possibilities you find, you choose, you will always find a solution. And with 4, you can see that it's not true. So try to find how can you avoid, how many possibilities, and you cannot have a solution that is monochromatic with 2 colors. So the minimum number will be 5. This was the question, that the theorem. And okay. And what happened when we have this kind of equations? So when we have this kind of equations, with what does it mean, this kind of equation? That doesn't matter the coloring, you will always find a monochromatic solution. But if you color all the positive integers, so if you color all the possible integers with K colors, and you always make sure you have a monochromatic solution, I will call this equation a regular equation. And we saw that the simple equation that we in the past example, that it was one of the regular equations. What about this equation here? So we can find a number of colors that if I color all the positive integers, I always find a monochromatic solution for this equation. And the answer is yes. And 2 colors are enough. So this was proved in 2016. So 2 colors are enough to color all the positive integers. And doesn't matter how random is your coloration, you will always find one monochromatic solution of this equation. So again, I hope you get the feeling that Ramsey theory, it's about finding order, about among apparent cause. And what is this order? Is finding structures with some color, with some property, doesn't matter, depending the property that you are looking for. And what does it mean cause for this, in this case? It means that I don't know the position of the points, I don't know the coloring that I will choose, I don't know in the game who player will start, etc. So if we don't know much about the starting conditions, can we predict what we get? And this is kind of the finding the order. So this was some, So Ramsey theory, again, studied the existence of monochromatic structures in colored universe. Or in other words, because here we're coloring, but it's not about the colors, it's about the preservation of properties in some partitions. So we saw some examples that are related to this theory. So I hope you refresh memory with these examples, with these problems, and you can see that there are some problems that are easy to understand, easy to explain, but once you take it a little bit further, not much, like we saw that we started with 3, and then when you are asking the same question for 5 or 6, we don't know the answer. So we can have this kind of problems, and I hope you have the feeling that in Ramsey theory, the important is to optimize, to know when it can happen, but also to optimize when it can happen. So it's these two parts. And I talk a little bit about what is the Ramsey theory on graph theory, but you can go through other areas of mathematics and you will find similar, not similar, the Ramsey theory in that area that deal with more, I wanted to say chaotic structures, but another approaches. So here we are dealing with graphs, with finite things, but you can have this theory in infinite graphs, in random graphs. We talk about two colors, finding monochromatic structures, but we can also ask multicolor structures and so on. So this is a theory that is used in many other areas of mathematics, and not just the abstract part and the theoretical part, but is also inside these areas, you can find applications. I found just these ones. Of course, if you are dealing with big data and you want to know structures, networks I mentioned before, so it doesn't have to be in a party, but all the social media, all the data that nowadays AI has, for example. So there are many applications of this theory in real life, let's say. And just to mention, Ramsey theory wanted to, or the development of Ramsey theory was to try to find some order or to try to find some structure. But we also have the anti-Ramsey theory, which mainly the idea is that complete order is impossible. And in this case, I mean, the feeling is, I mean, for me, you don't want things that are monochromatic, but you want things that are with all possible colors, for example. But still, you're asking for some structure, so it will feel that you also want some order, but okay. So this is just that you have in mind that you can find for structures that have one color, but nowadays with Ramsey and anti-Ramsey, you can ask for different structures, different colors. The limit is the sky. So, and just to mention, we started with this question: what chaos or order mean? We saw some examples for Ramsey theory, but of course we have the theory of the chaos in dynamic systems. So it's not just in things that were here. If you go in other areas of mathematics, you will find different meanings of chaos, but I think in general or the philosophy is to don't know what will happen or don't have enough information or don't have some order. So still, I have the feeling that it's not the same in all the areas, but what chaos means is don't having the information, or why we don't have this information. Certain variables can mess with your order, can mess with your results. So I think this is the feeling of chaos and order in general. And as I mentioned, just very few random numbers are known. However, this doesn't stop people keep working on them, try to solve them, but also in the process, or failing or trying, you can find other problems and develop other kind of theory. And I think this is the life of a mathematician. And I would like to stop here and thank you for your attention.